Hello, we are Igor Araus, Agustín Budd, Zilong Lu. In this video, we're going to show you our process and the homework we've done on simulating the synchronous machine using Plex. On class, we saw that the dynamic equation of the synchronous machine can be described using these following equations. Working a little bit with the mathematics, we can transform this equation into the following block diagram. This is the Plex schematic that we developed. Here we can see the electric machine on the control parts and how the different voltages and currents couple with each other. Here we can see the mechanical side representing the viscous load. If we plot this, we get the different reference values compared with the real values. As you can see, the ID current doesn't affect the angular speed of the machine. You can also see that the currents do converge with its references, indicating the correct functionality of the design. We can also see on the XY plot the relationship between the Q voltage, the D voltage, and their angular speeds. Now implementing a PI controller to control the torque of the machine in reference to the desired torque or torque reference, we implemented this following schematic. As you can see, instead of directly controlling the IQ current, the reference torque is compared with the real torque using this PI controller, thus obtaining the new IQ current. Looking at the plots, we can see that they still converge onto their desired reference currents. And plotting the different torques, we can also see that the reference torque is indeed driving the real torque to converge on it.
In this item we add the speed control. We can see it here that we add the velocity reference in RPM. Here we applied the different steps of velocity for different times. And here is the PI control that we do. The output of this controller enters to the PI of torque controller. Then this output enters to the current controller. So we are applying the cascade configuration of the three controls. Then we can see the results in this graph. I'm gonna to simulate again. We can see that the green graph is the speed measurement. Then if we spread the signals, we can see the reference of speed. So if we again do this, we can see that have a little overshoot, but you cannot see the difference between the reference and the measurement. So it's controlling good. In this section we added the synchronous machine permanent magnet model, where the parameters are the same that are in the datasheet, and this flux induced by the magnet that is constant is the same that the default value of the Simulink model. After this we add the H bridge system with a DC voltage of 220. And here we have the measurement of the three-phase current. So if we simulate, we can see that this is a three-phase system of currents, and for the control we need to use this transformation. First we use the alpha beta transformation and we obtain a biphasic system, and then we need to use the alpha beta to DQ system. And in this case, in this transformation, it's important to use the pair of poles adequates. In this case are one pair of poles. So the axis reference of the DQ is rotating synchronous with the machine rotor. So if we see this, we are gonna see constant values of the current. Then after that we can go to the control. Here we use the same model with the steps for applying the reference current, and here we can see that the EQs, the IQ and ID calculated here. Then we enter to the PI controller. There is no D, so it's only PI. And the output of this PI is gonna give us the modulating voltage for the IGBTs. We can see that we obtain a constant, relative constant voltage modulating because we are in DQ. Then we need to go to alpha beta, and we're gonna obtain a biphasic system of voltage. And finally, we're gonna obtain the modulating voltage in ABC. This needs to be normalized because the signals that enter to the SPWM needs to be between -1 and 1. So we are here is are normalized between the values. Then the modulator is a sinusoidal PWM, and here we can have the triangular wave with a MF of 500. And here we do the comparator with the camera and the modulator. Then it's important to not short circuit the same leg, so here we are doing that. So the signals that come from this modulation, we're gonna activate or deactivate the IGBTs. And we can see the result of the control in this scope, where the upper graph is ID and low graph is IQ. Again, we can see here in real time the simulation and how the IQ follows the reference. It's the same with ID. Here we can see that there is a little perturbation in ID when the IQ changes, because they are coupled. Here we can see it also, and here we can see another perturbation, and the simulation finished. So the control is correctly being applied.